We're going to look at the definite integral now. So the only difference between an indefinite integral and a definite integral is that we have these numbers here, right? So we can do something a little different with these. It's a little bit more specific. So this says use the formula for area of a circle to evaluate the integral from 3 to 6 for this function here. We can do one of two things. We can use a graphing utility to graph it, or we can maybe do it by hand, because why not, right? I can plug in some values for x, and I can get some function values out to plot, the old school way, right? So we're only looking from 3 to 6, so I wonder, will these numbers work out nicely? Let's do 3, 4, and 6. If we need more, we'll get more. So I'll plug in 3. Leaves me with 3. And then if I plug in 4, 4 minus 3 is 1. So, square root of 8. Not a fun one. What about 6? 6 minus 3 is 3. 3 squared is 9. Okay. 6 is 0. 3 is 3. 1, 2, 3. And the square root of 8, that's between the square root of 4 and the square root of 9. So it's between 2 and 3. So probably somewhere here-ish. And if it says area of a circle to evaluate, and that probably means if I plug in 0, I should get probably 0 as well. 0 minus 3, yeah. I get 0, and my picture is terrible. But I think that's supposed to make a perfect circle. And clearly, that is not a perfect circle based off of my drawing. But I can tell you it's going to be a nice little half circle there. So the area of a circle, we should know, is pi r squared. And if we're only looking from 3 to 6, then that's a quarter of a circle, because that's a half a circle right there. So we'll do pi r squared divided by 4. Our radius of this circle is 3, right? So pi times 3 squared divided by 4 is going to be 9 pi over 4 units squared. But not all integrals are going to be nice geometric shapes for us. So what can we do to help with that? And we'll get there eventually. Okay. I have to introduce this idea of a negative area, because so far we've been talking about integrals as being area under the curve. And we've usually done it as area under the curve above the x-axis, right? So we got to talk about negative area. So if I had some function that looks like this, right? This would be a positive area. And anything below the axis would be a negative area. Okay? And when we do an actual integral and do the math with the actual function, it does account for all of that. So we don't have to worry about it. But just unless we're looking at a picture. Okay, so there's a lot of space here, so I can kind of piece together this integral. So dx, we know, is the variable of integration. F of x we know is the function, but as a technical term, it's the integrand. It's the function we are integrating. B is called an upper limit or an upper bound. And A is the lower limit or lower bound. Okay? So at least to begin with here, we're going to look at some geometric shapes. So use the graph to evaluate each of the following. Note the graph consists of line segments and a semicircle on that interval -8 to 13. So all right, the area under the curve from 0 to 7 is going to be this shape here. It's above the axis, so it's positive, and that shape is a trapezoid. So we can find the area of that trapezoid Remember that geometric formula? 1/2 the height times the sum of the bases, right? So let's see, we got 1/2 the height, which is 4. And then the two bases, so 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7. And then we can do the math here. So 1/2 of 4 is 2, and then 10, and 2 times 10 makes 20. All right, 0 to 13, I have that first area part, right, from 0 to 7, that's 20. And then the rest of this is another trapezoid, and it's a negative area, so I'm going to subtract it off. So let's subtract that area. So 1/2 the height this time is 3, and then one base is also 3, and the other is 1, 2, 3, 4, 5, 6. So let's see, 6 plus 3 is 9. 9 times 3 is 27, and that's going to be 27 over 2. Just go ahead and make that 40 over 2 to combine that. So is that going to give me 13 over 2? All right. Then we want to go from -6 to 0. -6 to 0 is this semicircle, so that's going to be pi r squared divided by 2. Let's see, the diameter is 6, so the radius is 3. So 3 squared, and then pi over 2, which will give me 9 pi over 2, but it's all under the axis, so that's going to be a negative 9 pi over 2. All right, from 3 to 3 for the function, where's 3? There's no like width to any shape there from 3 to 3. So we actually just have an area of 0, right? All right, so one thing that we should have noticed so far is all of my bounds have gone from left to right. 0 to 7, 0 to 13, -6 to 0, right? But look at this one. I'm going from 7 to 0. So I'm going to erase my drawings up here. I'm going from 7 to 0. Right, I'm going in the left direction. At some point, I remember saying in the semester that going forward is the positive direction and going left or backwards is the negative direction. So it's still the same trapezoid that we had at the beginning. But because we're going backwards, or we're going to the left, even though it's above the axis, that direction is telling us we are negative, or the opposite. It's going the opposite direction. I same idea with F. We're going from 10 to 4. So let me erase these drawings here. From 10 this way to 4. So I would still take the area of these shapes here, but then I'm going backwards. So really, I'm doing the negative of the forward area. That idea is going to come up later. So let's find these areas, and then we'll just throw a negative in the end. So let's just do it here. So I would take this area here. So 1/2, the height is 4, and the two bases are 1 and 1, 2, 3. 4 and 4 makes 16. 16 divided by 2 is 8. And then let's do this one. We got 1/2 the height is 3. One of the bases is 2, and the other is 1, 2, 3. So I have what? 5. 5 and 3 is 15, so 15 over 2. So if I'm doing it forward, I have 8 minus 15 over 2. So I'll make that 16 over 2 minus 15 over 2 to give me 1/2. But that's going forward. So going backwards just makes it a negative 1/2. Right? All right, from -8 to 13. All right, that's across this whole thing. So we have a bunch of areas already. Then we have that semicircle. So that -9 pi over 2. We have that one trapezoid is 20. And then we have this other trapezoid, which was that -27 over 2. So the only thing I have left to do is this triangle here. And so triangle is base times height divided by 2. So 2. And then 1, 2, 3, 4. And divided by 2 is just going to leave us with 4. And then let's combine. So let's make everything over 2. So I got negative 9 pi over 2 plus 40 over 2 minus 27 over 2 plus 8 over 2. And then let's combine some numbers. So 40 minus 27, we know is 13, plus 8 is 21. So we can make that negative 9 pi plus 21 over 2. And leave that here. All right, so now we're going to switch gears a little bit and go for some derivatives. Just for fun. So I'm going to erase these drawings off of here. All right, so I want the derivative at negative 6. So right here. Okay. So we have a change in function here. We're going from a line segment to a semicircle. So the derivative is not going to exist, or it's undefined, I should say, because it makes a cusp right there, because it's changing in function. So it's not a smooth curve there. All right, we want the second derivative at positive 6. Well, the first derivative, I am on a function here that does have a derivative. So remember, it's just slope. So the slope of this function is negative 2, or that piece is negative 2. And it's constant, right? So then the derivative of that is just going to be 0. And the average rate of change over the interval 0 to 5. That is just the slope between those 2 points. So f of 5 minus f of 0 over 5 minus 0. So let's go find f of 5 is 4. And f of 0 is 0. So the average rate of change is 4/5. All right, got a few more concepts here. So we have some properties of integrals, and we've been kind of applying them in that above section, but let's just formalize them here. So we have looked at mainly the idea that from a to b for f of x dx is that from a to b, a is less than b, right? 0 to 1, 0 to 7, 0 to 13, that kind of deal. So let's look at some other cases. So what if they're the same, or what if it's that a is greater? So if it's the same, then that area is always going to be 0. There's no width to a shape there. If it's switched, so if that lower number is higher than the upper number, remember we just do the negative of the forward direction. Okay. We have some additive properties. So we can split it up if we need to. If we're looking at the area from a to b for f of x, let's say there's a point in the middle between them, kind of like where those two trapezoids were, right? I kind of separated it and said, let's do the positive one, and then we'll do the negative one. And we can do that because of this additive property here. Yeah, those are the same as what we've been doing. So, all right, let's see if we can apply some of these properties. So for a to b of f of x, we have 8. A to b for g is negative 3, and a to b for h is 5/2. So from b to a is just the negative of a to b. So if a to b is negative 3, then the opposite, or the negative of that, is just positive 3. 2 is a multiplier, so it's going to be 2 times integral of a to b for f of x dx, which is going to be 2 times 8, which will give us 16. All right, 5. It's one of those that's just a constant here, so it's going to be the constant times b minus a. We have a sum here, so we can separate it and say a to b for 5 dx plus from a to b g of x dx. We just did 5. And then g of x is what, negative 3? So we can make that 5 times b minus a minus 3. Here we have these subtracted. So integral from a to b for f of x minus the integral from a to b for h of x dx. So f was 8 and h was 5 over 2. Let's make that 16 over 2 minus 5 over 2 to give us what, 11 over 2? All right, we have from a to 4 for h and from 4 to b for h. So as long as these are the same, as well as these functions being the same, we can combine them and say that's a to b for h of x dx, which is 5 over 2. Right. Couple more things here. So we have this idea of odd and even functions. There's a cool little property here that can help us out. So even functions, let's see. We know that from 0 to 3, the area is 8. So what would the area from negative 3 to 3 be? And I'll just draw a function that's an even function. First one that comes to mind for me is x squared. And the property for even functions is that they're symmetric to the y-axis, right? So if I'm going from 0 to 3, and that area is 8, if I'm going the same distance the other way, I'm going to have the same area. So it's the same. So 2 times 8 is going to be 16. Now odd functions, the odd function I think of is y equals x. They are symmetric to the origin, right? So if I go from 0 to 3, saying that area is still 8, and then I want to go negative 3 here, it's actually going to be negative 8, right? It's going to be the same, just in the opposite part. So actually the area will be 0 here. So it's cool to know if you're doing symmetries. But, I mean, if we had the integral from negative 1 to 3, you know, that's not going to help too much because it's not going to be that same area. All right, I have this idea of average value of a function. So let f of x be continuous over the interval a to b. Then the average value of the function f of x on the interval a to b is given by 1 over b minus a, and then the integral from a to b of f of x dx. Right, average is just dividing by the number of terms, right? So if I have a function, and let's just use this part here. Let's say we're going to go from 0 to 6. So, okay, I can find that area. Let's just say it's 10. And then if I want to find the average, right, I'm going on an interval from 0 to 6. So I have like 6 spots to take care of. So 6 minus 0 is 6. And 1/6 times 10 is 10/6. I can reduce that, but that's just an example. All right, so let's do one with the actual function. So find the average value of x plus 1 over the interval 0 to 5. So we can use, let's see, 0 to 5. Oh, you know what? We haven't learned a rule yet. So let's look at the graph. X plus 1. It's going to look something like this. We're going from 0 to 5. So the shape that this is going to make is a trapezoid. So 1/2 the height is 5 times the base, the sum of the bases. So 1. And if I plug in 5 into the function, I get 6. So 1 plus 6 is 7. 7 times 5 is 35. So 35 over 2 is that area from 0 to 5 for the function. So then I just need to do the average value. So 1 over b minus a times that 35 over 2. So b minus a is the 5 minus 0, so 1/5 times 35 over 2. Well, 35 divided by 5 is 7, so our average value is 7 over 2. Okay. Okay. Looking here right quick. Let's see if I have something here that I thought I would have. And I don't. Okay. So I have to add a piece of information here. Sorry for all the scrolling here. Because at this point we would have done the substitution already, but then we haven't like actually evaluated them. So here's what I'm going to do. I'm going to give a rule here. So from a to b of some function, right? We know that if I do the integral, that's f of x, big F of x, and then plus c, right? Well, when we have bounds here, we can actually do this cool thing here. We can evaluate it like this. We can substitute in the top one and subtract off if we substitute in the bottom one. Okay. So when we do substitution, we have to change our bounds. So really, I should do a different example here. So let's do from 0 to 1 for, how about 2x plus 4. All right, so we know how to do the integral, right? That's going to be 2x squared over 2 plus 4x, and then plus c. I'll clean that up just a little bit. We're going to make that x squared plus 4x plus c. But because I have bounds here, I'm actually going to evaluate it from 0 to 1. And I do a straight line there to say I'm evaluating from 0 to 1. So I plug in 1. So 1 squared plus 4 times 1. And I subtract off if I plug in 0. So 0 squared plus 4 times 0. So 1 plus 4 is 5. And then 0 and 0, it's going to make 0. So if I just evaluated this, and I got 5. So the problem is when we have substitution, we have to change the bounds. Well, we don't have to. I'm going to show you that you can. I am going to, I'll do 2 of them changing the bounds, and then I'll do 2 of them without. So, okay, if I do my u sub, right, I have u as 1 minus x squared. Du is going to be negative 2x dx. I just have x dx, so I need to divide both sides by negative 2. So negative 1/2, and then I have the integral of u to the 1/2 du. And then now, because I'm in terms of u, I need to change my bounds. So instead of 0 to 1, I need to change that. So if x is 0, u must substitute in 1 minus 0 squared, which is going to be 1. Now I need to do it for the upper bound. So if x is 1, my new u is 1 minus 1 squared. It's going to give me 0. And then notice what happens. My new bounds are from 1 to 0, which is backwards, right? So I have to apply a property and switch it and take the negative of it. So I really have positive 1/2 from 0 to 1 for u to the 1/2 du. And then I can do the integral. So I've got 1/2 times, and then it'll be u to the 3/2 times 2/3. And then I'll evaluate that from 0 to 1. So I'll clean it up here. Those 2's will cancel out. So I have 1 to the 3/2 over 3 minus, if I substitute in 0, so 0 to the 3/2 over 3. That'll give me 1/3 minus 0, which is just 1/3. Okay. Do another one. So u is 1 plus 2x squared, and du is going to be 4x dx. Need to divide both sides by 4. So this becomes u to the negative 1/2 du. And then I need to change those bounds. So instead of x being 0, that new bound is 1 plus 2 times 0 squared, which is 0. So it's 1. And then if x is 2, my new u is 1 plus 2 times 2 squared. 2 times 2 is 4 times 2 is 8 plus 1 is 9. And then I can integrate. So add 1 and then divide by the new power. And then evaluate from 1 to 9. So let's do a different color here. That reduces to 1/2, right? So I have 1/2 times square root of 9 minus 1/2 times the square root of 1. So that's 3/2 minus 1/2, which gives 2/2, which is 1, right? Okay, I'm going to show you that you don't have to change the bounds. Personal preference here. I personally don't change them because of situations like that first one where I have to remember, oh, hey, I have to switch it because of that being not in proper form. And somehow I sometimes forget that. So I don't like to change anything. So here's what I'm going to do. I'm going to say, hey, u is 1 plus x cubed because I need a u sub to solve this. So du is 3x squared dx. So I'm going to solve the integral of u to the 1/2 du, which is going to give me u to the 3/2 times 2/3. And I'll put it back in its original variable. So that's going to be 2/3, 1 plus x cubed to the 3/2. And then I'll evaluate that from 0 to 2, because now I'm back in the original variable, so I can use the original bounds. So I have 2/3 times 1 plus 2 cubed to the 3/2 minus, if I plug in 0, so 2/3, 1 plus 0 cubed to the 3/2. 2 cubed is 8, 8 plus 1 is 9, square root of 9 is 3, 3 cubed is 27. 27 divided by 3 is 9, 9 times 2 is 18. 1 plus 0 is just 1, and that's just going to be 2/3. So, all right, 18, let's see, it's 54/3 minus 2/3 to give me 52/3. All right, so all it does when you're changing the variables, all it does is uses a different expression here. I use the original 1 plus x cubed, doing the u sub and evaluating it from new bounds. This will become u instead. So it gives you the same answer. I just feel like it's less steps, just not have to change the bounds. Let's see what this one does. I'm hoping this doesn't give me a trig thing. Let's see, u is 1 plus 5x squared. So du is going to be 10x dx, so I just have to divide by 10. And then I'm looking at an integral of 1 over u du. So that's going to give me 1/10 natural log of u. And if I made new bounds, I could evaluate it. I'm going to put it in its original variable. So natural log at absolute value of 1 plus 5x squared. Plus, I don't need the plus c because I'm going to evaluate it. So it just depends on where you evaluate. I like to use the original ones because I'm in the original variable. So that's going to be 1/10 natural log of 1 plus 5. And then subtracting off 1/10 natural log of 1. Well, the natural log of 1 is 0. 0 times 1/10 is 0. So 1/10 natural log, the absolute value of 6. And yeah, that is all I have for this one. So if you have any questions, let me know. And then you're free to change your bounds if you want to, or you don't have to, right? Just make sure you're in the right variable. If you're sticking with u's, then you need your new bounds. If you're changing back to the original function, you don't have to worry about it. Alrighty.